Hello, students. So I want to go over the types of collisions really fast. Not too fast, but fast enough. The first one I want to talk about is perfectly inelastic collisions. This is where things stick together and stay stuck together. So if I draw that out in terms of carts, the result is these things stick, say there's Velcro on them and they just stick together. The result is going to be a big cart stuck together, mass 1 plus mass 2. So this is going to be 1 and 2. Right? So in terms of the momentum, on this side, we can write mass 1 V1 plus mass 2 V2. Remember, these are vectors. So right now we're doing everything in 1 dimension. Eventually we'll do it in 2 dimensions. But right now, each one of these gets a different term before the collision. And then after the collision, we have mass 1 plus mass 2 times V. And we'll just call it V final. Everything just goes on like this. Now there is a inverse of this, which I'll call 1A here instead of 1, instead of 2. Explosions. And the way explosions work, we start with an object, 1 plus 2, and it might be more, in an actual explosion is an object turning into a bunch of gas that expands. Here, this could be something breaking, or it could be, a spring between these carts and they fly apart. Then we get two objects flying apart. Over here, we know that we're going to call these mass 1 and mass 2 eventually. So here, this is mass 1 plus mass 2 with some initial velocity. And that momentum has to become the momentum of the parts. Mass 1 V1 final plus mass 2 V2 final. So what the explosion looks like here is that we take an inelastic collision, videotape it, and play the tape backwards. All right, we're taking our time and running it backwards. And so we undo what we would do in an inelastic collision. We make stuff fall apart. So now this is the thing. In either one of these cases, we can look at the energy. And what we realize is work has to be done somewhere. When these things collide, they make sound, they may give off light, they heat up. Internal energies change. There may be friction involved somewhere, but the gist of it is energy is not conserved in these inelastic collisions or in these explosions. Energy has to come from somewhere to split these up. Right? This thing, if it's sitting at rest, then it has zero kinetic energy. Put it on the ground, it has zero potential energy. When it flies apart, these things have kinetic energy. Something had to do work to drive them apart. So these types of collisions don't conserve energy in any way. I mean, energy is always conserved, but it means that there's external work. These things don't do anything special with the energy. Now I'll put in 1B here as a third type. Maybe I should have done it 1, 2, 3, 4. And I'll call these mushy, which means energy loss and momentum's conserved, but things don't stick together. All right. So this is just arbitrary collisions here. I'm not going to draw that out. The gist of it is, it's an example like we just worked through in the last video. This is a mushy collision. We know it didn't stick together, And we know the momentum's conserved, but we don't know anything about the energy. I keep mentioning the energy. 2 here is an elastic, or perfectly elastic collision. Things bounce cleanly. Now you probably ask, what does it mean for something to bounce cleanly? So the special thing about elastic collisions is the kinetic energy. Note that I said kinetic energy is conserved. So we can write equations, right? We're always going to write something like M1 V1 final plus M2 V2 final equals M1 V1 initial plus M2 V2 initial. Right? We're always going to write something like that. But we can also go in and write the kinetic energy associated with each object. So 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared is 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared. That's what I mean by kinetic energy is conserved, is whatever this sum is on the left side equals the sum on the right. And that has to be true when this is true. So if it's a perfectly elastic collision, this is true. If it's a mushy collision, only the momentum equation is true. And then these other cases are when it sticks. So basically, the thing to note here that's important is if you read in a problem that something sticks, you go with the ideas in the first 2 things, or something falls apart. If you're told that it's perfectly elastic, then you can do this stuff. Otherwise, you just do this blue equation. So we're going to pause for a moment while I go set stuff up, and then we're going to do some practice problems with these, and some problems that you probably would like to see developed out, and some other concepts.